So this is subject 3, Turing machines. And phrase structured languages. So particularly, you surely remember a canonical example of a language that was not context-free language and that we needed more power, more computing power in terms of this theoretical power we are defining mathematically. And this classical example was x n times, y n times, and z or z 1 n times. So here we have this language, and this is actually a phrase structured language. So we will be able to analyze or recognize this language by using a Turing machine. And also a Turing machine can do a lot of interesting things. Do you remember when we tried to validate sum and addition by saying, for example, 0, 1 plus 1, 0, and this was 1, 1, and 0, 1, 1. And we had a string like 0, 1, 0, 1, 0, 1, 1, 0, or sometimes we draw the 3 zeros here. And we said that this that our previous machines could validate if this was a correct addition or not, if you remember. And now we will be able to actually write these kind of things into the tape. Why? Because the Turing machine has, as before, same as before, has a tape, and this tape is infinite to the right. Remember that these suspensive points or these dots represent that this tape is infinite. And also we will have cells. Each one of these cells can have a symbol, and we still have a reading head, but now we will have also writing capabilities. So differently as before, now this head can read or write symbols. Additionally, now our head will be able to move right and left. So this is a very different machine in terms of what it can do, because it will have a finite number of states as before. That's what we symbolize by using these numbers. They symbolize a finite set of states. And at a certain point, we are on a single state, and now we will be able, as I said before, to read and write symbols from the tape, and also we will be able to move left and right. That's what is symbolized here. Perhaps this is better if you write left and right. So we mean here left and right, and here we have read and write. Okay, so how does this machine looks as a diagram? We will still be using, particularly at the beginning, the same set of arcs and states as before. Actually, this is a directed graph if you want to see, to compare it to a discrete mathematical structure. And we will have now two different symbols here for each one of the transitions. So we will have the same as before, an initial state like this one, and a final or accept state. Same as before, we can have this state, but now in this case, it will be called a halt state. So whenever we reach this state, we will stop, meaning that after this point, nothing can go out. For example, before, when we reached a state like this, maybe we had an X or something, and we could go out from this state. So differently from that, now our machine, whenever we reach a halt, we have to stop. No more processing is made after this. So this is also one of the differences of these machines. Also, we have two symbols here. What do they mean? This first symbol is the what we will be reading from the tape. Read from tape. And the second symbol will mean what we write to tape, or an operation, or operation. This operation that will be performed regards, it will be L or right, move to the left or move to the right. So we will have either a symbol from the tape or an operation, move to the left, move to the right. In this case, then we will read a B. If we read a B, then we can follow this arc. If not, we cannot follow this arc, and we will move our head to the right. When we reach this triangle, this will represent an empty space. Why do we use the triangle? Because whenever, let's suppose we have something like A, B, B, A, and then an empty space, empty, 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 all this, let's suppose they are empty. So they have no symbol in it. If I symbolize the empty symbol without using anything, then it will look like this. Of course, it is not clear. If I use the lambda as before, then we can think that we can just ignore the input and follow this arc. Do you remember whenever we have a lambda or an epsilon, it meant that I could ignore the input and then follow or not follow this arc. In this case, we want to ensure that this cell is empty. So it is different. That's why we need a new symbol. This new symbol will be then this triangle, or you can regard it as a delta, but actually it's a triangle that symbolizes an empty string. So if you want to write this string without drawing the tape, you can write A, B, B, A, and then a set of triangles, which mean they are empty cells. Okay, so far, I think everything is clear, right?
The only question is, so we cannot, for example, write some symbol and immediately move to the other cell. Cannot.
No, you're right, Dima, because either we move to the right or we write a symbol. If we want to do both, then we would need two arcs. Let's suppose what you are saying is write a symbol. Let's say I recognize an A, and then I want to move to I want to write a symbol, let's say B, and then I want to move to the right. As I have just written a B, then I move to the right. This is what you are saying. Then I'm doing both things, writing a symbol and then moving to the right. And this is the same, and I know it will be red because I have just written it. And also please note that whenever we have something like this, we are overwriting this A. Let's draw it and let's do a simple execution of this machine. Let's suppose we have something like this tape, and we have A, B, B, A, and empty spaces. So let's suppose we are standing on this cell, and then we start this machine. Also, please observe that we can run a Turing machine starting on any cell. That's why it is very important to say where I am standing. Yes, so before you execute any Turing machine, you need to know where you are standing on the tape, where you are starting. So let's suppose we start here, and this state says, okay, let's start the Turing machine. It starts working and it says, okay, I have an A, then I'll replace it with a B. And then it will replace this A with a B. Okay. And then read a B. Okay, yes, I have a B here. Then move to the right. And then I will move this head to the right. and then stop. That's it. The machine stops, and the new configuration of the tape is this one. If you want to write it using the same notation we have been using here, using this notation without drawing the tape, then we will have the original configuration was A, B, B, A, and please note that this is where I am standing on. I will symbolize in this notation with an underscore that my tape will begin here. And then after running the tape, our new state will be, our new configuration of the tape will be A, B, B, A. And that's it. Yes. So it is the same. One is drawing the tape and the cells inside it, and another way is not drawing the tape, and we will represent this head by an underscore. They represent the same. And also empty spaces if needed. Let's suppose we need to represent this empty space just like a triangle. How many triangles? Well, as many as you want, because you know we don't know what it is here after this. So maybe there are 1,000 triangles and we don't want to draw them, right? Okay, so now let's execute also this machine we have here. Now we need to clear this because otherwise you will get confounded. So it will be exactly the same. I will begin in a new sheet. So now I am copying it from the book, so you will have it a pretty drawing instead of my awful circles and arcs. So it's the same. Now imagine we have something like A, B, and then empty spaces, and that my configuration starts here. And now the question is, and you will find several questions like this, what will be the final configuration when I run this machine? Then we need to start. We start here, and we have an A. Then it says read an A and move to the right. Okay, we read the A and then move our head to the right. And now, again, we have an A and then move to the right. We have the same and then move to the right. And then read a B and move to the right. Read a B and then move to the right. Here, here it is. So now I am standing here, and it says, if you find an empty space, write an empty space. Actually, it will just leave it as it is because it is writing what it is already writing. So it will leave it as it is and then finish and then halt. That's it. So you can see now that also we are not accepting or rejecting a string, not yet. That's something we will need to define. We have not defined what does it mean to accept a language in terms of a Turing machine, because a Turing machine can do a lot of more things than just accepting or rejecting a string, because now it can modify the string. Now it can modify the tape. So also there is a difference in concept in these terms. So as a formal definition, now we have a sextuple of this form. Here it is. A sextuple of S, which is a finite collection of states, same as before. We have sigma. Sigma is the set of symbols called the machine's alphabet, and these symbols cannot be blank. So that's why it says non-blank symbols for sigma. And similarly, as pushdown automata, we will have a gamma here, an uppercase gamma, Greek gamma, that is a finite set symbols, including those in sigma, meaning that it will be always a subset of that, and that are called the machine's tape symbols. And always this symbol will belong to gamma. which is the blank symbol. It's not the same as empty string or empty symbols as before. Just let me remind you. Remember that this is empty string, and we will keep using it. This is empty string. This is empty symbol, epsilon, and this is blank symbol. So the difference between empty symbol and blank symbol is that the empty symbol can be skipped. It doesn't matter if there is a symbol or not. We can just ignore it. However, when we want to ensure we have a blank symbol, then we will use this symbol. That's the difference. This can be ignored, and this cannot be ignored. By using a triangle, I must see it on the table. If I don't see the blank symbol, then I won't take it as a blank symbol. Okay, I think that's clear. And also we have delta, which is the machine's transition function. And the same as before, please remember the definition of deterministic finite automata. And also remember the definition of push-down automata. Please remember the difference in this delta. If you need to check your notes, please do it. But I want to tell you, if deterministic finite automata, what was delta? In the case of push-down automata, what delta was? Tell me the difference between this delta in DFA and push-down automata.
Well, maybe the difference is that there is no delta in the push-down automatons. Instead of delta, there is a T. That is a collection of deltas, I think.
That is called, sorry?
That the T is a collection of finite transitions.
Okay, yes, very good. Actually, that's the main difference, and that's the important part of that. That we have here that it's a collection. And as you correctly pointed, it's called T, a set of transition. And in this case, it's a function. And okay, let me add another question. Oh. No, this is not working. And no, it's not working. Let me add another question to this. Also, we had something called NFA, you remember? Non-deterministic finite automata. So in this case, what do we have for delta?
We have more than one. I don't know how to say. It's not determinate. So we have more than one steps to follow.
It's non-deterministic. Yeah, that's what you are saying, right?
Yes, it's non-deterministic.
Yeah,
So
right,
we have,
Emilio. And
yes.
regarding delta, can you tell me if this delta in NFA is a function or a collection?
It's not strictly a function because a function sets in correspondence to one value exactly one another value.
Right.
But here we can have several possible results of delta.
Right. Right. Then it cannot be a function. Then it has to be a collection. Let me recall the definition. So this is the definition for a non-deterministic finite automaton. We are talking about NFA. And let's compare this definition with a deterministic finite automata. So this is DFA. And today we are focusing on this part. I am asking you about delta, and you tell me, well, yes, there is no delta here. Here they call it rho. And this rho is a subset, and this is a function. And now let's compare with the push-down automaton. Let me search for the definition so that we can have all the elements in order to compare this. Here it is. So we are comparing definitions because I want you to see an important question here regarding the deterministic and non-deterministic features of these machines. In this case, as we have been told before, we don't have a delta, but we have a T. In this case, we focus on this part, and this says a finite collection of transitions. By collection, we mean set. So in this case, we have a set. In this case, we have a set. In this case, we have a function. And whenever we have a function which goes from S cross sigma to S, remember that a function maps, for example, something that says, given that I am on state 1 and I see an A, then I need to go to S2. And if I want to define this function, this transition function, again, let's say, if I want to say, well, but also you can go to state number 3. What you see here that this is not possible, right? Because a function must have only one output, the same output for the same arguments. So this is the essential definition of a function, that whenever you have exactly the same arguments here, you need to go exactly to the same result. The result should be the same. Yeah. So this is the definition of function. What does it? How can I do this? Well, then I can change into a set. If I define a set such as saying, well, I can have S1, then A, then I go to S2, and also I can create another set that says, when I'm in S1 and there comes an A, I can also go to S3. Yes, so by this means I can represent this, but then delta cannot be a function. It needs to be a set. So now that we have seen the difference between one and another, we can see that deterministic finite automata are, of course, as the name say, deterministic. And non-deterministic finite automata are non-deterministic. Wow. Okay, so what can you tell me about push-down automata? Are they inherently deterministic or non-deterministic? I let you think 1 minute. Okay, so do you think? Do you remember that we saw some properties of push-down automata and that we wanted them to be deterministic? They lost some properties. There were some languages that could not be recognized. Actually, if you do a deterministic push-down automaton, then we have the class of LR analyzers. You remember that? So push-down automata are inherently non-deterministic. Right? Then I want you to map this. Whenever they are deterministic, we have a function. Whenever they are not non-deterministic, we have a set. Here we have a set, so these are non-deterministic, right? And now the golden question is, are deterministic or non-deterministic Turing machines? Or better, are Turing machines deterministic or non-deterministic?
I think there is deterministic because it's a function, it's a transition.
Right.
Function.
Yes, yes. Exactly. That's what I wanted you to find, that Turing machines, because of this definition, are deterministic machines. So we go back again. Our DFAs, the first languages, regular languages, were deterministic. Then context-free languages are non-deterministic. And then these kind of languages that are called context-free phrase structure languages are, again, deterministic. So the only non-deterministic languages are the context-free languages. And even so, we work with them in compilers. Why all this occurs? Well, by definition, because the people who created them like this. Okay, so let's continue studying the properties of the definition of a Turing machine. But we will have an initial state called iota, and also the halt state. So what does also this definition implies? Can I have more than one halt state?
One second, Professor. But can we just like what prevents us from, for example, looking at this Turing machine that is on the screen and creating one more transition that would make it non-deterministic?
Nothing. Actually, we can add this to our Turing machine, changing this if we don't have a function but a set here, and yes, you will have a non-deterministic Turing machine, and they do exist. However, as in this case, remember, we had non-deterministic automaton, but there were always an equivalence to deterministic finite automata. So whenever you had a non-deterministic finite automaton, you could always convert it to deterministic. However, if you had a non-deterministic push-down automata, you cannot always convert it to a deterministic one. That's what we say, that push-down automata are inherently non-deterministic. More than the machines themselves, we are talking also about the languages they recognize. Here, DFAs recognize regular languages. NFAs recognize the same, regular languages. And therefore, because you can always take a non-deterministic finite automaton into a deterministic finite automaton, then regular languages are deterministic by nature or by definition, which is better. And then you can say that a push-down automaton, you cannot convert it into a deterministic automaton always, and therefore the languages they recognize, which are context-free languages, are inherently non-deterministic.
I see why.
So regular languages are deterministic, and context-free languages are non-deterministic. And now we are inferring for our new language we are defining by using a Turing machine. We are defining, or we will be defining, not yet, but we are able to define a set of languages called phrase structured languages. And these will be, in turn, inherently deterministic. Why? Because of this. And going back to the question, yes, you can define a non-deterministic Turing machine, but there is a procedure that can convert any non-deterministic Turing machine into a deterministic Turing machine. And maybe we will see that in the future. Yes, Camilo. No, okay, because you unmuted yourself, so I thought you wanted to speak. Don't worry. Okay, so we have a iota. Sorry, it got disconnected. Let me see. So I'm just trying to reconnect. Can you see my whiteboard? I think yes.
Now we can.
Okay. So continuing with this definition, we have this iota, which is the initial state. And also we were doing the question. We have a halt state here. So by definition, we cannot have more than one halt state because it says the halt state, right? So there is only one halt state. Okay, so now that we have seen the definition, we need to define a way of accepting or not accepting language. For this, let me follow the example from the book.
Hola. Bien, ¿y tú? Sí.
So before doing so, I want you to show another example so that this is very clear. I will use this same example. Let's do exercise number 1.
Ah, no, no te preocupes. A veces cuando no te puedo contestar es porque estoy en sesión.
So this is exercise number 1. We have the configuration of the tape as this, as we have been doing. And the question is, with what tape configuration will the Turing machine represented below halt if it started with this configuration? So I want you to give me the answer, please.
Bueno, cuando me dan la respuesta, por ejemplo, esto es para iteración.
I think that is in the number 5.
I think that the string will remain the same, and we will be located at the second triangle. Professor, you're muted.
Thank you. Yeah, Dima, I was saying that yes, maybe the string is not changed. We will execute now. I think Emilio had a question, but I couldn't hear before because there was some noise here.
I say that I guess that the machine stopped in the letter number 5 or Dima says in the second chunk.
Yeah, I think you're right. So let's execute it. Let's suppose we have done this XXX. I'm just drawing it again. And also we can draw this as an arrow just to make it more visible, but it's the same. So we have an we are here, we have an X and it says move to the right. Then this is moved to the right. And now we are standing on this state. Then we have another X, then we go back to this state and move to the right. And then we are here. And again, we need to move to the right. And again, we will end up into this state. Because we move to the right, then our head is here. And it says then if you find a triangle, which is the blank symbol, then you move to the right. Then again, move to the right. And finally, we have here, and it says, if you find an empty space, then write an empty space like this, and then halt. And that's it. That will be the end of this string, of this execution. So please note that it's important that the machine does not end here, but here, right? Because there is a final blank and then move to the right. And then this is not moving the head anymore because it's just reading a blank and then writing a blank. That does not move the string, correct? So if you thought this, then you're okay. If you thought something else, then just please check that this is moving just once and this is not moving to the right. Once you have this, then then we can continue. Let's do another exercise. Now you will have to draw or to create a Turing machine that has different symbols, and it needs to search for a pattern and stop if and only if this pattern is found. So this is exercise number 2. Our alphabet is X and Y, and gamma will be X, Y, and the empty, the blank symbol. And it needs to start, whenever it starts, whenever it finds the pattern X, Y, X, Y, halt. If not, then do not halt. Think that you can have also a Turing machine running forever.
I assume the string on which the symbols are written is infinite. So after some,
so because it's infinite, maybe you can never find the pattern, and then your Turing machine will be running forever. And
no,
that's
actually, I
that.
was worried about the opposite situation when the last Y was the last symbol. There's nothing after that.
Very, very far away. Well, maybe yes, you need to run for a long time before you find the pattern. Yes. Yes, Christian, Camilo. Okay, let me copy your solution. It says like this, and then like this, XR, XR, YR, Y, XR again, and then YR, and then stop. And whenever it finds something different, here XR, and then YR. And then there is a crossing here we will try to avoid. And we have XR. Okay, that's it. Thank you, Camilo. Please check if I copied it correctly. Maybe my drawing is a bit ugly because I tried to make it very quickly, and also I tried to avoid this crossing, which you did here. By the way, this is a very interesting issue, the crossings of these machines, because you can also define a completely different kind of machine just by saying if you need to avoid these crossings or not. There are also theorems and lots of studies regarding this. It's just like a mathematical problem. But well, we would not deal with this. We just don't care about crossings. I just avoid it because it looks not so nice, but don't worry, it's okay, Camilo. Then what Camilo did,
it's
and
not complete.
yeah? What's missing?
It
No,
looks
in
like
the,
it's not updating.
in the sharing, we can only see 2 states.
Oh, let me see what's happening here. Oh, I have just drawn it completely. This is interesting. Let me share again. Give me a second, I'm changing my, well, it's supposed to share now. I think there it is. Okay, now it's complete. So I think that most of you did a similar solution. So I will explain this. It goes here, it starts looking for X, Y, X, Y, which is the pattern we want to observe. If for some reason the pattern is broken, like X and then X, X, X is practically starting to look again for an X. And then if we have X, Y, and then another Y is found, then we need to start looking for X again for the whole pattern. Then that's why this arc is returning to the beginning. The same here, if we are about to find the pattern X, Y, X, but something appears like an X, then we need to start again looking for the pattern. And finally, if we find a Y, then we will stop and halt the machine as defined, as described. Okay, then this solution is correct. And I think this is defined for all states, for all possibilities, meaning that we know what will happen if we have an X here, but what happens if we have a Y here? What do you think it will happen?
It stays in there in the first state in a loop.
Well, I think it should. Yeah. So before I come to this part, Christian has his hand raised. So please, Christian.
Yes, one question, Doctor. Regarding the empty symbol, do we need to make transitions for that?
Okay, good question. Let me see what exactly it says. It says X, Y, and empty. Yes, it should skip also the blank symbol. It's not the empty symbol. Remember, the empty symbol is this. This is empty symbol. And this is empty string. And this is blank symbol. So they are almost the same. Just don't forget this. And yes, we should consider also blank symbols. So whenever the pattern is broken, yes, we need to start looking for it again. So yeah, that thing is missing. Coming back to the question of what happens if we have a Y here, we need to make it explicit. We need to write it here, Y goes to right, because we have not yet started to, we are not seeing the pattern yet. So we need to go back. So now this is defined for X and Y. This is defined for X and Y. This is defined for X and Y. And finally, this is defined for X and Y. So I like this part because it allows us to see what happens if I do not draw. By default, what would happen if we have this? Before we had something which was the pit. You remember the pit. In this case, Turing machines work differently. For whatever is not explicitly defined, then we will assume it goes to halt. And it does not move the head anymore. So if we have a Y, we will write a Y and then halt. So all Turing machines will halt for anything that is not defined. So this is very important because this works differently than the pit. For Turing machines, there is no pit, there is halt. So in the case of the machine that Camilo designed, because it didn't say what will happen with a Y, starting with a Y, it would just stop in that way. Now that we know what to do, then we know we need this loop here. Yes, so please take into account that this Y and this Y are options, are two different options. It's not, we cannot make this machine non-deterministic. Remember that Turing machines are deterministic. Okay, so I think this is clear. So maybe Christian is working on the solution considering empty, the blank symbols.
Yes, I can share my solutions. Let me take a photo.
Yes, thank you.
Yeah, okay, doctor, I already shared my solution in the chat.
Thank you.
Sure.
So I think everyone can see it, right? So that you can just open it, or I can also paste it into our whiteboard. Okay, here's the solution proposed by Christian. Can you hear me? Yeah, okay. So here he was taking into account what happens with an X, Y, X, Y, which is the backbone. Remember, when we are working with this, we first need to see the backbone, what we are being asked to recognize. So the first part is recognizing X. Well, this is okay, X, Y, X, Y. This is the backbone. Once we have found it, then we consider all the other options. As we know what will happen with X, then we need to see what happens with Y or what happens with blank symbol. So these are these transitions made for. Then whenever we are here, if we have a blank, then we need to go back to start here. If we have an X, then we can stay here. And finally, if we have a Y, we advance. In this state, we have an X, which will advance, Y, which breaks the pattern completely, and also blank space breaks the pattern completely. For this one, if we have an X, we break the pattern, but we do not go back to the first state because it's like if we have seen already an X. So this is correct. If we see a Y, then we stop. And if we see a blank space, then again, it gets the pattern gets broken and we need to start again. And finally, this is a bit dark in the picture, but I think you can see it. This is a halt state, right? And now you can see it a little bit better. So this is it. I think now you handle much better Turing machines. And also this is very important that for whatever is not defined, we just go to the halt state. And also there is no moving to the right. We just read something and leave it as it is and then halt. This is very important, this part. So please remember it. Okay, so we have solved several exercises. Do you have a question on this part?
Yes, I have a question.
Yes.
What if we only have a tape with X, Y, X, Y, and that's all? And you say we can start reading the tape wherever we want. So what if we start reading in the Y? Maybe we
yes,
can
the Y,
move,
okay, here, right?
yeah, maybe we can move left just to see if there's an...
Yes, that could be an option. It's not usual.
Okay.
If you start here, for example, then you will just miss the pattern and go Y, X, Y, and then you will find, I think, blank spaces forever. If you assume you will have it blank forever, or maybe you will have other stuff here, maybe X, 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 Y, Y, X, I don't know, but never the pattern, and you will run it forever. If you want, of course, you can implement the solution of moving to the left and then start looking for the pattern. The problem when moving to the left is that you never know how many cells you need to move to the left.
Yeah.
In this case, it's just one. But if you move another one, then you will break the Turing machine, and they are very expensive, and you don't want to pay for a new one, right?
Okay.
So that's called abnormal termination. Whenever you go back to the left more than when the tape begins, because the tape has a boundary to the left. It doesn't have boundary to the right. It's infinite to the right. Actually, this is not a big, it has not a big implication on the languages it can accept, but it's only infinite to the right, not to the left. Then if you move passed beyond the start of the tape, you will cause an abnormal termination. And it's better to avoid this. I mean, this is not a useful feature of Turing machines. Another option is whenever you want to move to the left, is the first thing you do is write a symbol here. Maybe there are other things to the left, but you write a symbol here, and then whenever you move to the left, you verify you don't go past this symbol. This is a strategy you can implement. Yeah, so the problem to your question is, yes, you could move to the left in order to capture the whole XY, but you don't know how many cells you need to move, and therefore you just miss the pattern. You assume that you will start looking from the point you are starting on, and whatever is to the left, you just ignore it. You won't see it.
Okay. Thank you.
Welcome. Okay, so now, because each time
Sorry.
Emilio is...
I have a question.
Yes, please.
2 questions.
As many as you want.
The first, in the first diagram,
Yes.
you say that we have 2 options. Yes, we and right, and y and y.
Okay. I mean, not that if you don't define this, then this is the default. If you define this, then this you cannot write it.
Okay, so it's either one or
yes, because Turing machines cannot be, well, yes, they can, but the ones we are seeing now are non-deterministic. Yes.
Okay. And in the second, what happens if we have XY, black symbol XY? This is the pattern or not the pattern?
XY, yeah, let me use different color. You say XY, blank symbol XY. No, this is not the pattern because it's broken by this one.
Okay.
And the exercise says only XY, XY. If it says, for example, find the second instance of XY that can be separated by any number of blank spaces, then we need to design a different machine that allows as many blank spaces as we want. We just ignore them and then find another instance of XY and then stop. But because what we are being asked here is we'll search its tape for the pattern, and this pattern does not allow blank spaces. So in this case, it's very clear, and you will have if and only if that pattern is found. That's why in this case, we will not allow a blank space here in between. That's why also, whenever we have this blank space, is not the same as this, right? Because if you have empty string, you can have as many empty strings as you want. So you can have, for example, XY, XY, and this is equivalent to XY, XY. Perhaps there's a confusion. You are, well, not confusion, but the question you have. Or even you can have as many of empty strings, and it will always reduce to this, because this can be removed if you want. This you cannot remove it, never, because if it says one space is one space. If it says two spaces, it means two spaces, specifically two blank symbols. That's why this symbol is different from this one.
Okay, thanks.
Welcome, good question. And well, now we will begin to create more complex machines. And for this, we will create some basic machines. For the machines we create, we will assume that we will have only three possible symbols: X, Y, and the empty and the blank symbol. And this is important because we can model any language by using only two symbols and a blank symbol. You can imagine this is a binary definition, 0 and 1. And of course, if you would like more symbols in the future, like X, Y, Z, and T, you can always number them and have this is 0, 0, 0, 1, 1, 0, and 1, 1, right? So always, it doesn't matter how many symbols you have from the beginning. You can represent any number of symbols you want just by using two symbols and a blank space. So that this is why for the following examples, we will assume that we will have only two symbols, X and Y, or 0 and 1. If you go to Zipser, Zipser will begin always with 0 and 1, and we will use most of the times X and Y, but it's the same. It's just, I want to stress that you can do anything you want with only two symbols, okay? Well, so we will define a machine that whose purpose will be just moving to the right. For this purpose, it doesn't matter if you have a Y and an X. It doesn't matter if you have a Y, and it doesn't matter if you have a blank. It will just always move to the right. And of course, you can draw the equivalent machine that would be called a left. So this machine is called R. If you want, you can draw machine L, which it doesn't matter whatever it comes, it will just move to the left and then halt. So these are very simple machines. Why are we defining them? Because they will be our construction blocks for a way of defining more complex Turing machines. Now we can define another machine that whatever it doesn't matter what it is there, it will just put an X, and this machine is called X. So we will have, it doesn't matter what is it there, it will write an X. It doesn't matter if there's a Y, it will write an X, and it doesn't matter what is it there, it will write an X. And you can find the same machines for Y. Give me a second, sorry. Okay, sorry. Okay, so we have the same, the machine that writes an X, machine that writes a Y, you can draw it by yourselves, and also the machine that writes an empty symbol. It doesn't matter what it's reading. And also, there are some machines that are allow us to find an X to the right. Let's say we will call this machine find the first X to the right of the current cell. So tell me something, because I don't know if my headphones are correctly connected after the call. So tell me yes or something.
Yes.
Okay, I can hear you. Thank you. So find the first X to the right of the current cell. And because it says to the right of the current cells, the first thing this machine will do is move to the right, no matter what it comes, an X, and then a Y, or a blank space, and then it will keep moving to the right until it finds an X, and then it will halt. With this sample, also you can find the first Y to the right of the current cell, and also you can find the first space, blank space, to the right of the current cell. So you see, we have several basic machines: R, L, X, Y, blank symbol, find the first X to the right of the current cell, find the first Y. Yes?
In the second diagram, you are looking for the second X, right?
No, I'm looking for the first X to the right, because let's, yeah, that's a good question as well. Let me clarify. Let's suppose you have this X, right? XX, or even better, X, Y, Y, X, Y, Y, and you are standing here. And it says, find the first X to the right of the current cell. So the first thing it does is move to the right. It will ignore completely this one. It doesn't matter if it's an X, a Y, or a blank, it will just ignore. And then it will move to the right, and then it will find this X and then halt. So this is why you are asking, well, this is the second X, right? In this case, yes, if there is an X here, it will be like the second X in the string, but it's the first X to the right of this cell, because it will just ignore whatever there is in this cell. Yeah?
Yeah, thank you.
Okay. So you can draw the same machines for RY, R blank space, and also you can draw the same set for all the left ones. Left, find the first X to the left of current cell. Find the first Y to the left of the current cell, and find the first blank space to the left of the current cell. So these will be all of our basic blocks. Can I change page?
Mm-hmm.
Okay. So let's draw RY. First, you will move to the right, whatever it comes. And then you will move to the right if it's not a Y. Then if it's an X, move to the right. If it's a Y, move to the right. Unless it's a Y, then you keep it and stop and halt. Now let's write this in a new way of that it's called block diagram.
Professor, maybe yes. One of the arrows that goes from the second state to itself should be the blank symbol.
Thank you. That's it. Now we can draw this as a block diagram, and this block diagram will execute machines in order. For example, if you want to write an X and then move to the right and then write a Y, we could just write it like this. And this will execute machine X, then machine move to the right, and then machine write a Y. You can see why this is much more complicated when we try to use the usual diagrams, because in this case, we would need the X machine that whatever there is, it writes an X. and then concatenate it with the right machine, that whatever there is moves to the right. And finally concatenate it with the Y machine. Whatever there is, write a Y, even if there's a Y already. There we have. Then you can see how much simpler is this notation than all this notation, right? So from now on, we will start using this kind of notation. For this, we can define machines such as Rx in this way. We will have this part that says, the first thing you will do is move to the right. And then if you find a Y, then again, move to the right. If you find a blank space, move to the right. And do you remember what happens if I do not define something in a Turing machine?
We go to hold state.
Right, it will stop. Meaning that when will this machine stop?
When after moving to the right, we find an X.
It will stop whenever it finds an X, right? And let's draw this machine as well. We have this machine move to the right. It will keep moving to the right whenever it finds an X or a blank space. And I want you to compare now this machine this machine and this machine. They are the same, just with different representation. This is called the standard diagram. And this is called the block diagram. And palitos y bolitas means something as stick and circles. But this is, of course, this is joke, so don't take it serious. So you can see the block diagram is much more simpler. It's much simpler. And also we will do, we will create more machines. For example, move to the right if you find anything different to X, until you find something different to X. So it will be like this. Move to the right. I think this notation is very nice, and it allows us to move to a different representation, which is also much more, well, the power is the same, but I would say it's more powerful in terms of conciseness. It's much more concise, the block diagram.
I have a question, Doctor. In the block,
Yes,
in the middle, the block in the middle is the first.
This?
Well, no, the previous one. Yeah.
This.
Yes. This part. I think that I have a question.
Yes.
The second block is read until you find y, right?
This. No. I think, yeah, your question is right, because I'm not drawing properly. So let me make a zoom. This would like a big R and a small Y. And in this one is an X, an R, and a big Y, you see? So this is my fault for
Okay.
not drawing properly. This is sub Y, R sub Y. In this case, this is not sub Y, not sub
Yes, okay,
Y.
okay.
Sorry
Thanks.
for that. Yeah, sorry to confuse you, but it was my fault for not drawing properly. So whenever you draw a sub, it means move to the right until you find a Y. And in this case, it's move to the right and then write a Y.
Yeah, thanks. Yeah. Thanks.
Well, thanks for your question and clarification.
So, teacher, I have another question. Can we concatenate the block diagrams?
Yes. Precisely, that's the next thing we are going to do.
Okay.
So I'm just about to complicate your lives a little bit more. I'm just waiting for you to synchronize with the whiteboard. And whenever we are ready, we can proceed. So is there anyone still copying? No, okay, so let's go ahead. Now I will create a new machine called shift right, where we concatenate these block diagrams. This is called shift left. And shift left will, as the name implies, shift the string to the left as if I'm pressing the super or the delete key. Yeah, the suprimir or delete key. You know, whenever you write, you have a string and you press delete, the string moves to the left, right? So if you have something like, oh yeah, no, and you are standing here, then you will move this L and you will have hola, right? If you press the delete key. So this is the purpose of this machine, work as a delete key. So we will start by writing a blank space, no matter what there was before, and then moving to the left. If at this point we find a blank space, then move to the right and stop. Then I will add a new kind of notation. It's called, if at this point you find an X or a Y, you will keep it as a omega. It's just, it's similar to a variable. When we execute this, this will be clearer. Then move to the left. If at this point you find an empty, a blank symbol, then you will move to the right, write a blank symbol, and then move to the right until you find the next blank space and then write omega. This omega is the same symbol we found here. If we found an X, it will write an X. If we found a Y, it will write a Y. This is just to avoid drawing this again. So making these blocks simpler. We will go into that later. So on the meanwhile, don't worry. Now I will do this again. If you find an X or a Y, store this into what we will call sigma. This is a variable. Then move to the right, write this symbol, and then move to the left. In this case, if I found an X or a Y, it will be stored into sigma, and then I will write exactly that symbol. I will not write a sigma, but an X or a Y, depending on what we found at this point. Then go back here. Go back to this point. You will see there is no symbol here, meaning that it will always, whatever there is here, it will just move and then left again, meaning that it will go left and then left again, and then evaluate. If it finds an X or a Y, go this way. If it finds an empty space, go this way, and it will keep working. So now let's execute this so that it will be clearer. Let's suppose we have something such as X, Y, X, 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 and we want to eliminate this Y. So we start our execution. We start here, and it says, write an empty symbol. Let me let me copy this so that you know what was the original string and the new string. With red again. So I will copy this exactly the same. Okay, now we do the transformations. We are here, it says write a blank space. I'm standing here, so I will write a blank space and then move to the left. Now we are standing here. Sorry. If there is a blank space, then move to the right and stop, which is not the case. Then go this way. This way it says, if you find an X or a Y, which is the case, then omega will have this value. Then we just write here, omega was X. Now we are here. It says move to the left. Then move to the left. Oh my God, I just did a mistake. Sorry. Let me go back. And I will change some things on my diagram because I wrote incorrectly. So this is R, this is L, this is R, this is L, and this is L, and this is L, and this is R. Just a simple mistake. I just wrote everything reverse. Sorry for that. So, okay, so this is R, L, R, L, R, L, L. Okay, yeah, that's it. So please correct all your R's and L's in your diagram. Sorry for that. And let's begin the checking. I will write it properly. This is an R. This is an L. This is an R. And this is an L. L, L to the symbol, and then this is L. L, sigma, R. That's it. Sorry for that. So let's begin again. I just wrote L and R the reverse way. Okay, so now we recover from this mistake. Now we are here again. We are writing here. It says write a blank space. So we write a blank space and then move to the right. Then we move to the right. Here, if we find an empty space, then move to the left. That's not the case. This is an X. Because we have an X, then we will call this an omega. So we write here omega, it's equal to X. Why X? Because this is what we are finding here. If we had a Y here, then omega would be Y. But we have an X, so omega is equal to X. This is what it says here. If you find a X, omega will have this value. If we have a Y, omega will have this value. So we just write here the value for omega. Then move to the right. Then we just move to the right and we are here. At this point, again, it says if you find an X, this will be the value for sigma. If we have a Y, this will be the value for sigma. So in this case, we have an X, then sigma will be X. And then move to the left. Then we move our head to the left. And it says write the sigma. The value for sigma is X. Then we will write here X. It was already an X, but we don't, we just rewrite it again. And then move to the right. We move to the right. Now we are here and it says whatever there it is, it doesn't matter, or it would be the same if it's an X or a Y or a empty symbol, it's the same in this case. Then move to the right. If at this point we find an X or a Y, that will be sigma. I think I didn't move to the right, correct? So I think it's this one. Okay, so then if there is an X or a Y, that will be sigma. Then our sigma is an X. Move to the left. Write this sigma. Then move to the right. And then whatever is it, move to the right again. If at this point we have a blank space, then move to the left, we will go this way, which says move to the left, write a blank space, find the next blank space to the left, so this will be ignored, and then it will move up to this way. And then write omega. Omega is X. Then you write X. It looks awful, right? So I will copy the string again, and it will write X here. And finish, halt. Why halt? Because there's nothing else defined here. So what happened? Just imagine you pressed the delete key here. So you just eliminated the Y, and still there are 3X, 1, 2, 3X. We just eliminated the Y. This is the way this machine is working. It's a bit complicated, but I think if you follow it step by step, you will have clear what is working, what is doing. Now, Emilio, please.
Sorry, teacher, I don't understand the last step when we have a blank. Yes, in this case, we have to move to the left and then replace this letter with a blank, with a triangle.
Yes, it was.
And then
here, then it means find the first blank space to the left. Remember that we have a machine like this. It says, this machine says, move to the left until you find a blank space. Then we are here. we move to the left. This is not a blank space. Move to the left. This is not a blank space. Move to the left. This is a blank space. Then stop. And then write the omega. Omega is x. We write it here.
Okay,
X,
okay,
instead of the blank space.
okay. Thanks.
Welcome. More questions? So I will, now that we have this machine, I will, I think you are still writing. No. Yes. Okay, I think you are done, right? I will copy again. So here's the machine. I just want to show you what happens if you don't use this construction, because sometimes we tend to think, oh, well, this is a variable. So Turing machines use variables? No, it's just a diagram issue. In order to have to clarify what happens if we don't have this kind of tool, let me show you this thing. First, let's write separately what we have here. We have an x and we have a y in this case. Then for the x, we move to the right. Then again, we have an x or we have a y. If we have an x, then we do left x r and then go back to this point. If we go to this part, then we go left, right and y, and then go to the right and go to this part. For the y, I'm sorry, and in any case, if we have a blank space, we will write left, blank, left until we find a blank, and then right and x. Y and x, because this x corresponds to this x here. Now for this other part, we will have move to the right, and if we have an x, we move to the left, and then write x and move to the right, and then go back. Or if we have a y, move to the left, write a y, and go to the right, and then go back here. And if we find an empty space, we will have left, blank space, left, until you find a white space, and then write a y. This y is this y. And this x is this x, this y is this y, this x is this x, and this y is this y. So let me just separate this because it's not conveniently placed. So what I want to show you is that these two diagrams are completely equivalent. In this case, we used some kind of variable to abbreviate this diagram. It says, if you find an x or a y, then it will be later referenced as an omega. This omega is this omega. In this case, this omega, which there is no omega here, this x is the same as this x. So x, x, omega, omega, or y, y, omega, omega. I want to show you how this diagram is just synthesizing, or not synthesizing, abridging, making it shorter, the diagram. And then here we have again two options, x or y goes to sigma. And that's why I draw it in green, because this, whatever we find here in this sigma, it will be taken here, sigma, sigma, which is x, x, or y, y. Or in this case, the same, x, x, y, y. So if you don't want to use this kind of constructions, the kind of constructions that I will do this and this, then you would have to repeat the whole diagram. So I expand this not because I want to make your life more complicated, but because I want you to realize what is this doing? How is this helping us? And that Turing machines do not have variables. I think this is the most important part. Turing machines do not have variables. Because this looks like a variable. No, it's just a diagram thing. Okay, and finally, in the 10 minutes we have left, I want to scare you. Yes, because I want to show you this beautiful diagram that looks like very much like a circuit diagram. And I like it very much because it's very useful. And instead of drawing it step by step, we will execute it in order to show you what it does. So we will take a string, which is XX, Y, Y, Z, Z, and see what it happens. We will begin our operation right there. So we will, I will copy this in order to work on it the same as before. I will destroy this string, right? As I will need more space, I will move this upwards and this will upwards as well. Okay, so the first operation is write a hash. So this is a very destructive method because we will end up eating up this string. Then move to the right. Then we will move to the right. Here we are. Then if you find an X here, shift left. Shift left, remember, it's like pressing the delete button, the delete key. So we will just eliminate it. And now we are standing here. We did this, shift left. Then if we find a Y, no, we find an X. It doesn't matter how many X do we find, we just skip them. In this case, we have just one X. We skip it. If we find a Y, then shift left. We will eat it again. So shift left. In order to eat it, we just do X, Y, Z, Z, delta, blank, blank. Okay, so we killed it in this point. And if we find more Ys, we just skip them. Don't eat them, just skip them, move to the right. And then until we find a Z. If we find a Z, then again, eat it. In order to eat it, then we will just shift it to the left. X, Y, Z. And then we have something like this. And after we eat the Z, it says, if you find a blank space, no. If you find anything that is not a blank space, then go to this point. You will go to the left until you find the hash. So meaning you will do move to the left, move to the left, move to the left. Ah, there is a hash. Then we stop here. Okay, then we begin here again. Move to the right. We are here. And then if we have an X, eat it. That means shift to the left. We have successfully eaten it. If you have a Y, then eat it. Then we will just shift to the left. If we have a Z, eat it. When I say eat it, I mean eat it. Then we eat this Z here, shift to the left, and we will have something like this. We have just killed our string completely. It says, if you find a blank space, move to the left. Then our head will be here. If there is no hash, then eternally loop. This is an eternal loop. But because it is a hash, then stop. So we will stop for this string. And that is a good thing. Because for Turing machines, stopping means accept. Whenever we stop after reading completely a string, it doesn't matter if we destroy it. If we are able to stop after we have completely read it, it means the string will be accepted. Then accept. If at any point we have something that didn't match what we expected, for example, if we have X, then again, let's see a Z, X, Z, then go to this eternal loop. The eternal loop means the machine will never stop. And if the machine never stops, it means it won't accept the string. Let's write in a different color. If the machine does not stop, means it does not accept the string. Yeah, so we are seeing here a different way of accepting or not accepting a string. If we read the string completely and then stop, it means the string was accepted. If we, after reading the whole string, or even part of, after reading the whole string, we never stop, then it means the string is not accepted. So Turing machines are a strange kind of machine because they can only accept. If they do not accept, just they do not stop. This will define if a string belongs to a language or not. Now, not to continue with this strange conundrum, we will say that this the kind of strings that this machine accepts is precisely xn, yn, zn, with n belonging to natural numbers. So now it's up to you to verify for other strings how they are not accepted by this Turing machine. This Turing machine is designed so that whenever the pattern is broken, the pattern of x, y, z is broken, it will just keep looping and looping and looping and looping eternally. So now you can imagine how many machines are still running in the universe. That's terrible, right? Okay, so next class we will take this again. We will review it again so that it gets, it has to be completely clear because it is very important. And also we will clarify on the kind of languages that can be defined by using this method. So apart from using Turing machines for creating or writing different things on the tape, they will be used as the previous machines for accepting or rejecting machines. Okay, so now homework for next Tuesday.